Hi everyone, welcome back after the break. We're going to be continuing on in MATA35, and we're going to be talking about direction fields, autonomous ODEs, and the phase line. So we spent all of the last lecture talking about exact differentials, integrating factors, and linear first-order ODEs. We're going to talk about a completely different kind of ODE, one which we introduced a couple lectures ago, the autonomous ODE, and we're going to give some qualitative methods for understanding what's going on, as opposed to these explicit methods for finding an actual solution. So what we have is we're going to talk about first-order ODEs and the slopes of solutions. So if you have a first-order ODE, you can write it as a y prime is equal to f of x, y, where f is some function of both x and y. But now, remember that the derivative can be thought of as the slope of a function, right? So if you were to have some example ODE, so for example, if you had some ODE y prime is equal to x plus y, then that means that a solution passing through initial conditions, or just passing through the point, y of 1 is equal to 1, has slope y prime is equal to 2. Because here, of course, that's the x value and that's the y value. And so this is passing through the point at the point 1, 1. Okay? So if you were to draw this out, we don't know much about the overall solutions, but what we do know is we can draw out on the x and y axis, let's say this is 1 and this is 1, then at the point 1, 1, we know that the slope is equal to 2. Similarly, you could also figure out that a solution passing through y of 0 is equal to 1 has slope y prime is equal to 1, because it's x plus y, and so you might have a slope of 1 there. And so on. And so you can do this for every point in, let me delete this accidental marking. But yeah, so for every point in the xy plane, you know the slope of a solution that passes through that point, because that's exactly what y prime is. And, well, you can draw these things out. So, oh, whoa. What just happened here? Something went horribly wrong, but hopefully it is in the right place. Those things, I was supposed to delete those before. Yeah. Anyway, so a direction field graphs out the slopes of all solutions going through a point. We can visualize different solutions by drawing trajectories on curves that are always tangent to the direction field. Oh, that's what happened. It just went under. Anyway, I will redraw them now. But basically, we have all the different slopes at all the various points in the xy plane. And so, which we've drawn out here for y prime is equal to x plus y. And then for any solution curve, you can draw them out by just following along these lines. And so you're always tangent. So for example, we have this line here. So they'll always be tangent to a little line when you pass through it. Let's see, we have one here that is just basically a straight line. And maybe one here that's almost a straight line, but then it starts curving a little bit. Or ones that curve slightly more. Okay, so that wasn't a perfect drawing, but basically, these are all solutions. These are all different solutions to the ordinary differential equation y prime is equal to x plus y. So now I didn't give you an explicit formula for it, but these are the equations because you know what the slope is at any particular point in your system. And in fact, this is one of the ways that computers actually solve ODEs approximately, is you just draw out these sorts of solution curves by following along at what the slope is at any individual point. Does anyone have any questions about that before we move on? So this is a nice sort of graphical way of understanding the behavior of an ODE system. Okay, So moving on, that is for a general first order ODE. Let's talk about autonomous ODEs. So recall that an autonomous ODE is one that does not have an explicit dependence on the independent variable, that is, time. A first order autonomous ODE can be rewritten in the form y prime is equal to f of y. So we covered this a couple lectures ago, but just to give a couple examples, if we have y double prime plus y is equal to 0, this is a second order autonomous ODE. Or if we had something else, let's say we had, what color was I using? Black. Y prime squared minus sine of y minus 1 is equal to 0. This is first order autonomous. Oh, the bottom line doesn't look like it follows the dots. Well, if it doesn't follow the dots, that means that I drew it wrong. That is quite possible. So basically, whenever you cross one of these lines, you're supposed to be tangent to it. So something like that. And I apologize for not being a perfect artist. Anyway, going back to this, we have a first order autonomous equation, and of course you can rewrite these things. So you can rewrite this as y prime squared is equal to sine of y plus 1, and y prime is equal to the square root of sine of y plus 1. So this is in a more standard form. But it's still the same first order autonomous equation. Okay, so now importantly, note that if y prime is equal to f of y, then the slope has no x dependence. And so here I've drawn out the slope fields for direction fields for two different equations. One is y prime is equal to sine of y, and the other is y prime is equal to y squared. And so you have some number of different solutions here. So maybe you have this solution here. Just pretend that all of my curves are tangent to the lines when they cross them, because I'm not drawing them perfectly. And let's see. And in this case, it turns out that there will be a straight line here, but you just can't see it because it didn't draw out the direction field everywhere. Note that whenever you have horizontal lines, you end up with an entire horizontal constant line, because, of course, there's no x dependence, so if it's a horizontal line in one point, it's a horizontal line in the next point, and it keeps on going. So you end up with a number of horizontal lines. And those horizontal lines are actually quite special. Those are what we call equilibrium values because they don't change. So basically, if you're at that solution, then y doesn't change at all. You have an ODE with a constant solution of y is equal to 0, for example. So clearly, y is equal to 0 is a solution to both of these ODEs, are both solutions. And we call these things equilibrium values. So an equilibrium value of the autonomous ODE y prime is equal to f of y is just a constant solution, y is equal to some constant c. And we can solve for these by setting y prime is equal to 0 for, or f of y is equal to 0. So let's take a look at our two examples above, or on the previous slide. So if you had y prime is equal to y squared, well, we're setting that equal to 0. And so that implies that y is equal to 0 is the only equilibrium solution. On the other hand, there are actually a bunch of equilibrium solutions for the other one. So y prime is equal to sine of y is equal to 0. So that implies that y is equal to k times pi, where k is any integer. Are all equilibria. And if you go back to this previous one, you sort of see them because you see a set of lines where one of them are going down and the other are going up. And if I had drawn I probably should have drawn these direction fields in a little bit more resolution. You would have seen that there are horizontal lines across at pi and at 2 pi and at 3 pi, etc. Okay, so let's try it out. So what are the equilibria values? Let me reset my chat. For y prime is equal to y squared minus y minus 6. So remember that the equilibrium values are just all the points where y prime is equal to 0. So in order to solve this, you just need to set y prime equal to 0. Okay, so we're getting some question marks and some C's. So I'm going to try explaining that again, and hopefully it'll make a little bit more sense the second time around. So what we're doing is we're just setting, to find the equilibrium values, we set y squared minus y minus 6 is equal to 0. And so therefore we can factor that, y minus 3 times y plus 2 is equal to 0, and y equal to 3 and minus 2 are our equilibrium values. Does that make sense? So both of those happen to be equilibrium values. So all of the above. And what this looks like is if we look at here at 3, there is a line, and at minus 2, there's also a line. And another thing you might notice is that the other lines sometimes go away from and sometimes go towards these equilibria. So let me draw a couple other lines here. So for example, if I start here, what I'm going to do is I'm going to quickly go down to this, and then approach this other equilibrium. If I start here, I'm quickly going up and approaching this equilibrium. Whereas if I start here, I'm quickly running away from this equilibrium. I shouldn't have used blue. Let me use green. And let's draw another one. And so it turns out that this kind of behavior is very important. Whether these equilibrium values are the other trajectories go towards it or away from it, that is a very important classification. And if they go away from it, we're going to call it unstable. And if they go towards it, we're going to call it asymptotically stable. Because the x-axis here is time. And so basically what you're asking is, as time goes to infinity, do I approach my equilibrium points or do I not? And that is basically what it means to be stable or unstable. Away is to the, everything is moving to the right. In this particular chart, everything is moving in the positive direction of time. So that's this way from your angle. I should really stop mirroring myself because, yeah. So it's this way. So away is to the right. Let me write that. Direction of time. So this is a very subtle thing that Ken is asking. I thought time isn't a factor since it's an autonomous ODE. So what it means to be an autonomous ODE is that time is not a factor for the slope. For the value of y prime, time doesn't play an explicit role. But your system is still evolving, right? So for example, let me give a very simple example. Suppose that we have suppose that you have bacteria growing in a petri dish. How quickly they grow is dependent only on how many bacteria are currently present, right? Like, if I start the petri dish today versus starting it tomorrow, that doesn't actually change the growth rate. And so time isn't a factor explicitly. But of course, as time passes, you still have growth. So your petri dish still, after an hour, it might double in the number of bacteria, and after another hour, it might double again. So time still plays a role, just not explicitly. It's only implicit. Does that make sense? But yeah, so we still have a direction of time. But the point of these being autonomous is that you note that if you look at any particular horizontal slice of the direction field, all the values are the same. Whereas if you went back to look at our direction field for an arbitrary equation, even if you have a constant y value, as time changes, as x changes, your direction is in different directions. Whereas in all of our autonomous examples, that's not the case. And so that's sort of what we mean by autonomous. Okay, so let me go talk a little bit more about stability. So what does it mean to be stable? So let's consider an equilibrium C. So some equilibrium of y prime is equal to f of y, where we have some value c, and some initial value y of 0 is equal to y naught, where y naught is very close to c, but not equal to it. So if you wanted to, you could make this a bit more precise using an epsilon delta definition, but we're largely avoiding epsilon delta definitions in this class, so I'm just going to say if y naught is close to but not equal to c. Then c is unstable if y diverges from c as time goes to infinity. So for example, let's suppose I had my xy plane here. Let's say this is x, this is y, and we had some value c. So this is some equilibrium value. And then let's suppose we start off somewhere close to it. So if we start off just slightly underneath it here, then maybe it diverges. And maybe it like converges to some other point, but diverges away from c. Whereas if you start above it, maybe you go off to infinity or something. Let me do a better job of drawing that. Okay, so that's what it means for it to be unstable. So this is an unstable example. What does it mean to be stable? Or what does it mean to be asymptotically stable? Well, that means that as x goes to infinity, y of x goes to our equilibrium point. So that would look something like this instead. So let's say this is our c. We have our xy axes again. And suppose that we start off somewhere close to it, and it asymptotically approaches our solution. And maybe from over here, it also asymptotic from relatively nearby, or even from further away, maybe. It asymptotically approaches our solution. And so in this case, we call that asymptotically stable. Lastly, we're also going to introduce something called semi-stable, which is a little bit weirder. But in this particular case, if you start on one side, you approach it, and if you start on the other side, you don't approach it. So maybe here, you diverge away, but maybe here, you approach it. And this is what we call semi-stable. Okay, so what's the intuition behind all this? Suppose that you're, so for those of you who've taken physics already, one intuition you can think about is, think about a ball on the top of a hill versus the bottom of a hill. If you balance a ball at the very top of a hill, let me draw this out. Let's say we have a top of a hill and we have a valley over here. So if you balance a ball at the top of a hill, that is unstable because if you push it slightly to either side, it'll drop. But if you have a ball at the bottom of the hill, it's also in equilibrium, so you don't need to worry about balancing, because if you push it up slightly, it'll always go back down. And so this here would be unstable. This here would be asymptotically stable. I guess I can go ahead and draw another one for, let's see, let's suppose we have a something that looks, semi-stable is a little bit harder to draw, but basically if you push it to one side, nothing happens, but if you push it to the, let's actually draw that as a cliff. I think that's probably a good thing. So let's suppose that I had a cliff. And you have a ball precisely at this point here. And we're going to assume no momentum. And so if you push it on this side, it's going to go down, but if you push it in the other direction, it's going to fall away. But it is a stable point itself. So ignore momentum. And so this here is semi-stable. And in fact, one thing you might notice is that semi-stable is, in practice, generally relatively unstable, because if you push it in the wrong direction, then it will fall off and diverge. Does that sort of make sense to everyone? So now the question is, how do we determine the stability of each of our equilibria points? And there are a couple different ways of doing it, and one of them is just to look at the sign of y prime. So note that y prime is equal to 0 at an equilibrium. If y prime is greater than 0, then your slope is going upward, and that your slope is going upward and implies that y of x gets bigger. If y prime is less than 0, that implies that y of x gets smaller. So let's give an example. Let's use the same one we did earlier. Let's say y prime is equal to y squared minus y minus 6. So y prime is equal to y minus 3 times y plus 2. And let's see. So there's our vector field. And we have our two solutions. So one of them is at 3. And one of them is at minus 2. And looking at the vector field, you can tell which one is stable and which one's unstable, right? You can just follow along the trail. But another way you can tell is by looking at the sign of y prime. So let's say that in one case, so if y is less than minus 2, well, then we know that y prime is equal to, well, minus 2 minus, if it's less than minus 2, then this here is a negative sign, and this here is also a negative sign. And so we multiply those together, you get a positive sign, which is obviously greater than 0. And so therefore, when you're less than minus 2, you go up, which is basically what we see here. When you're less than minus 2, you go up. On the other hand, when y is greater than minus 2 and less than 3, we have that y prime. Well, if it's between minus 2 and 3, then this first term here is still negative, and the second term here is positive low, because it's greater than minus 2. So the second term is now positive, so we multiply those two together, you get a negative number, so that's less than 0. And so therefore, you go down. Sorry. Okay. Therefore, you go down. So, for example, even if you're slightly less than, you go down. And lastly, let me use, I guess I'll use blue. If y is greater than 3, then y prime, well, the first term is positive, and the second term is also positive, and so that's going to be equal to a positive number, so it's going to be greater than 0. And therefore, you have that it goes away because it's going upward, so it's getting bigger. And that's another way you can tell that this here is unstable, because when it's above it, it goes further up, and when it's below, it goes further down, whereas this here is stable. Now, note that the time dependence doesn't really matter, right? We aren't worried about how quickly it goes up or down, just whether or not it goes up or down. And so we can encode all of that information in what's called a phase line. We'll go over this in a bit. So note that I have turned my axes on the side. So originally my y-axis was the vertical axis. Now it's the horizontal axis. Since I'm only going to worry about my y values. And I'm going to separate it into these three regions. So -2, 3. And note that when it's less than -2, it's positive, and so it goes up. When it's between the two, it's negative. Y prime is negative, so it goes down. And when it's greater than 3, it's positive, and so it goes up again. And so therefore, this is unstable, and this is stable. Let's repeat that explicitly. So what we drew there is a phase line. So what we do is we draw arrows along the y-axis depending on if z is equal to f of y is equal to y prime is positive or negative. If the slope is positive or negative. So given some equation y prime, let's say, is equal to y to the fourth minus 4y squared, what you can do is we're just graphing out this entire function, y to the fourth minus 4y squared, where note that the y-axis here is horizontal and the x-axis, the vertical axis is some new variable we've defined, z. Well, then what we can tell is that here, when it's less than -2, this is positive. So if the equation is positive, then you go up. Here the equation is negative, and so you go down. Here the equation is negative, and so you go down. Here the equation is positive, so you go up. And so that implies that this point here, wherever it touches, where it's equal to 0, this point here is going to be unstable. This point here is semi-stable, because it is an equilibrium, but it goes in the same direction, both above and below. And this here is asymptotically stable. And it turns out we can encode those. So if z equal to y of x, f of y crosses the y-axis going upward at an equilibrium, then C is unstable. Then the equilibrium is unstable. So if you have it going upward like that, well, here you're going to be going down, and here you're going to be going up because of whether or not it's positive or negative. And this is the y-axis. If it goes the other direction, then it's asymptotically stable. And lastly, if it touches the y-axis but remains on the same side of the y-axis, then C is semi-stable. So I'm going to draw it twice. So the most obvious one is if you have like a parabola touching, but it can do all sorts of crazy stuff. Well, can't go that crazy because it is still a function. Do all sorts of crazy stuff, but if it just touches at a point and then goes back down, then that is semi-stable. Okay, let's try it out. So I have some function here. This is the graph of this function, which is y prime is equal to y to the fifth minus 3y to the fourth minus 4y cubed plus 12y squared. And I want you to classify the stability of the following equilibria. So note that the equilibrium points are all the points where it touches the y-axis, so the horizontal axis. So we have 4 equilibrium points, and now I'm going to ask you to classify the stability. So what is the stability of the equilibrium at y is equal to -2? Okay, so we're getting a couple of replies in. Okay, so it looks like most people have converged on B, that this is unstable. Well, when you see a phase line like this, one of the first things you should do is you should draw out the arrows along the y-axis. So let's do that. So below -2, is the function positive or negative? Well, it's negative, right? So that means things are going to be getting smaller. Whereas between -2 and 0, y prime is positive, and so things are getting bigger. Between 0 and 2, it's still positive, and so it's still getting bigger. Between 2 and 3, it's negative, so it's getting smaller. And above 3, it's positive, and so it's getting bigger. And so once we've done that, it's pretty easy to tell that this minus 2 here is actually unstable. And let me reset before going on. What about y equal to 0? Is that asymptotically stable, unstable, or semi-stable? Okay, yeah, so we're getting a lot of C's, and this is indeed semi-stable because it gets closer on one side, but goes away on the other side. And you can probably guess what I'm going to ask you to do about next. What about y equal to 2? Is y equal to 2 stable, unstable, or semi-stable? So note that I'm talking about this one here now. Okay, I'm getting more A's now. Sorry, I think that there's just a delay in the chat. Okay, but yeah, so this is actually, oh, did I not reset? Maybe I forgot to reset. That might have been the problem. So this here is going to be asymptotically stable. And let me make sure to reset the chat this time. And what about the very last one? Y is equal to 3. So is this stable, unstable, or semi-stable? Okay, so yes, it is indeed unstable. Okay, and you can tell, right? Because all you have to do is you have to look to see whether the arrows are pointing inward or pointing outward. If they're pointing inward, it's stable. If they're pointing outward, it's unstable. And if one arrow points in and one arrow points out, then it's semi-stable. Okay, so that involves just looking at the sign of y prime. There is another test that you can do, which is basically the same thing, but using derivatives instead. So there's also a derivative test for stability, which is if you have an equilibrium at C, you can take the derivative at df dy and if the derivative is positive, which means that your line is going upward, so this means precisely that you're crossing in this direction, then it's unstable. Whereas if it's negative, then that means you're crossing in the other direction, so it's asymptotically stable. And lastly, if it's a local extremum, so if it's a min or max of the function, like that, then it's semi-stable. Okay, let's give an example of that as well. And I don't know if I'll take the time to actually do all of these, but we have our original function. We know our equilibria points. So f of y is equal to y to the fifth minus 3y to the fourth minus 4y, I don't know why I'm copying this, minus 4y cubed plus 12y squared. So then what's df dy? Well, that's equal to 5y to the fourth minus 12y cubed minus 12y squared plus 24y. And we know that df dy of minus 2, well, we're going to plug all those things in. That's 80 plus 96 minus 48 minus 48, which is equal to 80, which is greater than 0. So minus 2 is unstable. Similarly, actually, the next one is a little bit more complicated. So if we take the second derivative, d squared y f, and we'll need the second derivative for that one. This is equal to 20y cubed minus 36. Minus 36y squared minus 24y plus 24. Oh, I am clicking on the wrong things. Minus 24. Hopefully I did that right. Plus 24. no, minus 24y plus 24. Well, when we plug in df dy at 0, that's equal to 0. And so, oh, we need the second derivative because, oh, sorry, I skipped a step. Df dy, if you plug that in, you'll find that that's equal to 0. But if it's equal to 0, then that means that it's a critical point. And so if you want to figure out if it's a maximum or minimum, then one way of checking that is by using the second derivative. And then d squared f dy squared is then equal to 24. So 0 is a local minimum of f of y. So 0 is semi-stable. Because remember, we need to use the second derivative to check to see if something's a maximum or minimum. And we can also do the same thing, df dy of 2. That's going to be equal to minus 16 after you solve everything. So 2 is stable. And df dy at 3 is equal to 45. So 3 is unstable. Okay, so this is another way of solving it. Sometimes it's easier to use the derivative test. Sometimes it's easier just to directly compute the signs in each of the different regions. So that is up to you, whether or not you want to take the derivative at the point or you want to take the sign in between the regions. They'll both give you the right answer. Generally. The sign test is actually more general than the derivative test. So you should do whichever one you find is easier. Okay, so let's try it out. And I'm actually going to give you, we're going to briefly dip back into the world of biology and biophysics, since we've been sort of in math land for a while. So, this is a fat crystallization problem. It's actually example 4 on page 568 of your textbook, and I just took it from there. So this is the Bittinger Calculus for Life Sciences textbook that we're using. So let y of x be the proportion of crystallizable milk fat in a sample after x number of hours, satisfying some autonomous differential equation y prime is equal to 8 times x y to the 5th minus y. If you start with half of the fat as crystallizable, how much fat is crystallizable as time goes to infinity? And let me reset the chat. So basically what I'm asking is, if this happens to be the autonomous differential equation defining how much of the milk fat in a sample is crystallizable, will they crystallize or won't they, or will it remain the same? Okay, let me give you a little bit of a setup. So, of course, the first thing you're going to do is you're going to take y prime is equal to 0 is equal to 8 times y to the 5th minus y. And you're going to have to solve for this. And so when you solve for this, you get 0 is equal to y times y to the 4th minus 1. So 0 is equal to y. 0 is equal to y times y squared plus 1 times y squared minus 1. So 0 is equal to y times y squared plus 1, y plus 1, y minus 1. Okay? So y is equal to minus 1, 0, and 1. Those are your critical points. Sorry, not critical points. Those are your equilibrium points. Looks like we have a lot of confusion. Okay, that's fine. So the first thing we have to do is you have to remember how we define the equilibria. We define the equilibria as the points where y prime is equal to 0. And so you just have to solve for that, and you have these are your equilibria, where y is equal to minus 1, 0, or 1. Well, the next thing you do once you have your equilibrium is, once you have all your equilibria, is you draw out the phase line, and you have minus 1, 0, and 1 as your major points. And now the question is, can you draw arrows between each of these different segments to determine whether or not these are stable or unstable? So when y is less than -1, okay, it seems like it's quite confusing to people, but when y is less than -1, is y prime positive or negative? You can reply in chat if you can figure it out. So in this region here, where y prime is where y is less than -1, is y positive or negative? Or sorry, is y prime positive or negative? Okay, yeah. So it turns out this is negative. And the way you do that is you can look at each of the different components. So here we have this y, right? So is y positive or negative when y is less than -1? So that's negative. This thing here is always positive, so we don't have to worry about that. That's always positive. This thing here, well, when y is less than -1, it's negative enough that y plus 1 is going to be negative. And y minus 1, well, when y is less than -1, that's also going to be negative. And so this entire thing is going to be equal to negative. And so therefore, this is an arrow that goes downward. In this region, it turns out that y prime is going to be equal to a positive number. And so therefore, you have an arrow pointing upward. And if you keep on doing this, you'll find that you have an arrow pointing downward here and an arrow pointing upward there. Okay, so this is just by using a sign analysis, you can figure out which direction the arrows point. But now that we figured out which direction the arrows point, let's go back to the word problem. Where are we starting? We are starting out at this point here, at 1/2. So where do we go? If you start at 1/2 and you're going along this line based on which direction the arrows go, where do we end up? Yeah, okay, so we're getting zeros in chat. Yes, exactly. So it has to go in this direction, and so it goes to 0. But then once it gets to 0, it doesn't leave it anymore because it's a stable asymptotically stable equilibrium. So the answer is actually C here. Yep. So I think I skipped a few too many steps there, but hopefully that logic sort of made sense. I'm going to give another example of this, and I'm going to walk through. I probably should have done these two in the opposite order in retrospect. But let's see another example of this, and we'll finish out the class today with the logistic growth model. So let's see. Come on. Go away. So in a previous class, we saw exponential growth. Y prime is equal to ky, y of 0 is equal to y naught, which has a solution that we explicitly solved for. Y of x is equal to y naught times e to the kx. But now, in practice, if k is positive, this is unrealistic, because bacteria in a petri dish will initially grow exponentially, but then they'll use up all the available media, and they won't be able to grow anymore. So a better model is this other model, the logistic model, where y prime is equal to ky times 1 minus y over L, where the parameter L is the carrying capacity of the environment, and k greater than 0 is still the growth rate. And given this equation, we can find the stability of the different equilibria. So the first thing we need to do is we need to solve for the equilibria. So y prime is equal to 0 is equal to ky times 1 minus y over L. So then y is equal to 0, or 1 minus y over L is equal to 0, which implies that y is equal to L. So we have two equilibria, 0 and L. Well, Now what we want to do is we want to draw out the phase line again. So we have 0 and L. And so now what we want to do is we want to figure out whether y prime is positive or negative in each of these regions. So in this region, we have y prime is equal to, well, this here, that's going to be negative, right? If y is less than 0. This here is actually going to be positive when y is less than 0, because then 1 minus a negative number is going to be positive. So this is going to be, oh, sorry, that's positive. So this is going to be a negative. And if that's a negative, then that means that this arrow points downward. Over here, what we have is y prime is going to be equal to a positive times a positive. And so that's going to be equal to a positive, and so this arrow points upward. And lastly, this here, y prime, is going to be equal to a positive times a negative. Oh, sorry. A positive times a negative, which is going to be equal to negative, and so this goes here. And so note that this means that the 0 is unstable, and the L is asymptotically stable. And what this means is if you start out at a particular point greater than 0, you'll grow up to the point L. So if you start at a point, actually let me draw this on the next slide, and this is our very last slide. So we have our y prime. If y is less than 0, this is not physical, since we can't have negative bacteria, so we don't have to worry about that. When your y is between 0 and L, y prime is greater than 0, so the number of bacteria are increasing up to L. On the other side of L, the number of bacteria decrease down to L. So on large timescales, the petri dish can support L bacteria. And so if we want to draw that out, let's draw our y-axis vertically again, and have our x-axis of time. If we have a y-axis and our x-axis of time, you could draw out the equation for this region, but of course that's 0, so this doesn't matter because that's not physical. And then what else you can do is, well, if you take the carrying capacity L, then what will happen is you'll start outgrowing exponentially, and you'll approach the carrying capacity, no matter what number you start out with from either side. And this is actually one of the most commonly used basic population models. So if you introduce an organism into a new environment, at first it's going to grow exponentially when it has lots of food available, but then there are going to be too many, and they're going to start using up all the food or the resources of the environment, and they're going to stabilize at some carrying capacity, at least in the logistic model. And even though you'll notice that we didn't actually explicitly solve for the solutions, but we can still qualitatively tell you what happens on long timescales because we can understand the asymptotic behavior using these phase lines. And with that, I think I will end today's lecture, and I will see you on Friday.